Okay, so this is the first lecture, and it will be available online, as well as the handwritten notes. So my suggestion is that you treat what's on the screen as the blackboard, and you take down the notes. I will save those notes and make them available as PDF, but I think there's some learning that goes down in copying down the notes as they're written. But then that's completely up to you. If you just want to print out the notes, the typed up notes, and annotate them as I go, then that's up to you. But it is quite helpful to go through the derivations themselves and write them down and find the mistakes as we go. I feel like there's one more point. So I recommend you print out the notes from the course, the typed ones, and I suggest you go chapter by chapter. And as we go through, we're going to find some small mistakes and typos in the chapter, and I'll keep updating them. So at the end of the course, the textbook, the full file will be updated. So I don't recommend you download the whole thing at once, because I might update future chapters before we get there. So just try to keep pace with the class. So today, we'll start with chapter 1. So is there any questions on the format? So we'll probably be able to finish chapter 1 today. This is just to introduce the formalism that we're going to use and the system of coordinates. Okay. So in introductory physics, you've learned to describe classical systems using Newton's law, Newton's second law, right? So far, can describe classical systems with Newton's second law. Newton's second law is a vector equation. It says that the sum of the forces equals ma. So this is a vector equation. And so what this really means is that this is 3 equations. It's 1 equation per component. And I mean 3 equations in 3-dimensional space. Okay, so every time you write out Newton's second law as a vector equation, you're really writing out 3 equations. You're writing out 1 equation for each component. Okay? So in analytic mechanics, so usually when I define something, the first time I put in quotation. So in analytic mechanics, we use scalars instead of vectors. To describe a system. And we'll see that this new approach of using only scalars is equivalent to Newton's second law. But mathematically, it's prettier and easier to write down. It also has some advantages. For example, the vector formalism, it can be very awkward to write down vectors, let's say in spherical coordinates, or describes the motion of a system along the surface of, say, a sphere, is awkward when you're doing with vectors. So analytic mechanics we'll just make that easy to do. So we think of a theory of classical mechanics. What do we want from it? So we want it to be able to describe a system, both knowing its current state, how it's going to evolve in the future, and how it's come to be from the past. So a theory of classical mechanics should describe the past and future evolution of a system. So we know that we can describe the current state of a system by specifying all of the coordinates that's my abbreviation for coordinates. Describe the current state of a system by specifying all of the coordinates of all of the particles. So that's what we mean. When we have a system, we mean there's a bunch of particles. And when we're asked to say, what's that system look like, if you specify where each of those particles are, we claim that that's what we mean by describing a system. So we can say where everything is, place all the blocks here, that's the current state of the system. Okay? So that's the first part. We also know that the future and past of the system is given, I'll run out of page here. We know that the future and past of the system is given by specifying the velocities of all the particles and the forces on them. Okay? So you have a system, let's say that system is a cannonball, and it's somewhere in the air. So you can describe the system by saying where the cannonball is, and you can know where the cannonball will be by knowing its velocity and the forces, say gravity, that are exerted on it. So the system is described, the current state, by the coordinates, and the future development, or the past, is described in addition by specifying the velocities and the forces that act on the system. Okay? So this is just formally saying stuff that hopefully you already know. Okay? So in vectorial mechanics, so Newton's second law, we use forces and accelerations. In analytic mechanics, use velocities and potential energies. And so as we'll see throughout this course, many systems are much easier to describe using the analytical mechanics approach than the vectorial mechanics approach. So let's do an example of that, of a system that's particularly annoying to describe with the vectorial approach. And maybe I'll let you finish it as an assignment. I haven't decided, because it is really quite horrific mathematically. So the system, this is example 1.1, so it's an example of something that's really annoying to do in vectorial mechanics. It's called the double pendulum. The double pendulum you have one mass, M1, attached to a massless and extensible rod of length L1. And let's say this makes an angle theta for later convenience. And then we have attached to that pendulum second mass, M2. And it's attached with a rod of length L, and it's inexpensive. Is somebody trying to get in? Okay, I heard it. And so, the question may be, describe the motion of the two masses. All right. So if we want to describe the system, what we really want is what we're going to call x1 of t, y1 of t, x2 of t, and y2 of t. So x1 and y1 are the x and y positions of mass 1. So let's put a coordinate system here. So if I can know the functions of time that are x1 and y1 of t, then I fully describe how m1 moves in time, and similarly for x2 and y2 and m2. So the goal of describing the system is to find the functions x1, y1, x2, y2. Okay? So the system is described, its current state, by specifying those four numbers, and the evolution through time is determined by specifying how those numbers evolve with time. Okay? So how would you solve this problem in vectorial mechanics? So you would start with Newton's second law. So Newton's second law you would do for each mass, right? So for mass 1, you have the sum of the forces equals the acceleration. So the acceleration of m1, so m1 a1 vector, is equal to the forces that are on m1. So right now you have to stop and you have to go figure out what are the forces on m1. M1, hopefully this is first year physics, so I hope I'm not losing anybody here, right? But please do ask me if you have a question, because for some of you it might have been a while since you've done a free body diagram or whatever. So we draw the forces on M1. So on M1 we have three forces. We have gravity, M1G, we have a tension from the first string, which let's call that T1. And then we have a force of tension from the second. I call them strings and rods exchangeably, but they're a rigid object that has no mass. Let's call that T2. So that's the forces that are on M1. So if I put that into the equation as a vector, then the sum of the forces is T1 vector plus T2 vector plus M1 G vector. So similarly for M2, we're going to have M2A2 vector is equal to the forces on M2. There's an M2G from gravity, and there's the same magnitude but opposite direction T2. Okay, so M2A2, the sum of the forces is T2 vector plus M2G. So technically it's not the same vector in these two equations, so one of them should probably have a negative sign. But I'll just keep that in mind when I write it out explicitly in components. Okay? So that's how you do it with the second law. Now you haven't really, remember the goal is to find out x1, y1, and x2, y2 as a function of t. Alright, so we need to know what the functions of t are. So x1, y1, x2, y2 don't even appear in this equation, right? So, let's make them appear. So this is a two-dimensional problem, right? So we'll say everything is constrained to the z equals 0 plane. So we actually have four equations here, right? So let's write out the four equations. So we're going to write out the x and y components of both of these equations. So let's start out with the x component of the first equation. So this gives so we have M1 A1x so if I look at T2, and I've introduced these angles theta and phi to help out with writing out the equation. The theta and phi depend on x1 and y1 and x2 and y2, right? Because this is x1 here, and this is y1 here, right? So sine theta is x1 over L1. So if I look at T2, its x component is in the positive x direction, and it's T2 sine phi, right? So I have, T2 sine phi, and then T1 is in the negative x direction, and so it's minus T1 sine theta. If I do the y component, I have M1 A1y. So T1 has a component in the positive y direction, that's T1 cos theta. T2 is in the negative y direction, so that's minus T2 cos phi, and then minus M1g. Okay? And we do for the second one, we have M2 A2x equals, there's only one force in the x direction for mass 2, and so that's going to be minus T2 sine phi. And then finally, we have m2 a2y, the y component of acceleration of mass 2, which is going to be t2 cos phi minus m2g. Okay. So how does this give us the functions x1, y1, x2, y2 of t that we desire? That's because a1x, for example, so these are actually second order ordinary differential equations for the functions that we want, for x1 of t, y1 of t, x2 of t, and y2 of t. Right? The reason these are second order differential equations is that a1x is defined to be d squared x1 by dt squared. a1y, is up at 3 equal signs, is d squared y1 by dt squared, etc. So these are 4 ordinary differential equations that specify the second derivative of our functions with respect to time. Now you can't solve this because you don't know t1 and t2. So there's something missing here. Basically there's 4 equations and 6 unknowns, right? So we have 4 equations and 6 unknowns. The unknowns are a1x, a1y, a2x, a2y, and t1 and t2. So what gives? But x and y are not independent. Right, so we haven't really found a way to describe how x and y are not independent. But if you look at it, if you know x, you know y, right? Because the length of the pendulum is fixed. So if I specify x1, given that this has to form a triangle where L1 is fixed, then I always know y1, right? So y1 is always equal to the square root of L1, which is a constant, squared minus x1. Okay? So we say that there's a constraint. That is the language that will formalize the classical mechanics. Is that x and y are constrained. They're not independent of each other. All right? So x and y are constrained. So let's make it. Actually, when I lied a little bit, there's really 8 unknowns, right? There's theta and phi in our 4 equations. But you know that you can express theta and phi in terms of x and y, so you feel okay with it. But technically, you don't know them either. All right. So if we want to work with the full-blown 8 unknowns, which are the 4 x's and y's, the 2 tensions, and the 2 angles, then we need another 4 equations. Okay? So we also have, so the constraint equations, I'm going to write them as, oops, oh, that happened. Still sharing here. Right. So I'm going to write out the constraint equations explicitly and say we have x1 is L1 sine theta, y1 is minus L1 cos theta, x2 is x1 plus L2 sine phi, and y2 is y1 minus L2 cos phi. Plus theta and phi, let's say. So here we have 4 more equations. Now, from a purely mathematical standpoint, you will believe me that we can reduce these 8 equations to 2 differential equations. So think of it, 8 equations, 8 unknowns, should be able to solve for everything. So remember, we're not solving a linear system, like linear algebra here. This is differential equations, right? So ultimately, you have to think of how many independent functions do I need to describe this system. Let's go back and look at our system. Where's my... This is still working. Where did the black working now? Let's go back and look at the system. So I said initially that we need to want to specify a system. We need to say what is x1, y1, x2, y2. So we specify those 4 numbers, tells us the current state of the system. So now I've already argued that x and y aren't actually independent. So if I know x1, I can figure out y1. If I know x2, I can figure out y2. That means I really only need 2 things to specify the state of the system. I could specify x1 and x2, or maybe it's more natural to just specify theta and phi. So this is a concept that we'll formalize in a minute, but it's the idea of degrees of freedom. How many degrees of freedom are necessary to describe the system? So there's 2 particles, and you would think that both particles need 2 coordinates, but the particles are constrained by these ropes and massless rods or whatever they are, and so that reduces the numbers that we need to describe the state of the system. And so in this case, we only need 2 numbers to specify the state of the system. So you would think that we should be able to reduce those 8 equations down to 2 differential equations. And there's no getting around the fact that this is a complicated mechanical system, and you're going to have to solve a differential equation to see how it evolves in time. In fact, this is a highly chaotic system. Finding the actual differential equations in the nice one is kind of ugly, but I'll get you started and show you what the progression would be. So, based on what I just said, we have only 2 degrees of freedom. So should get 2 ODEs to solve. Furthermore, we can choose what those 2 degrees of freedom are. Okay, so some choices are smart and some just don't make sense, right? So you can't choose x1 and y1 as the 2 degrees of freedom because it doesn't tell you anything about x2. Those are not what we call a generalized coordinate, a coordinate that fully describes the system. So we can choose the degrees of freedom, but you have to be a little bit smart. So we can choose x1 and x2, or I can choose y1 and y2, but let's choose theta and phi. So we can choose theta and phi to describe the system. So that means we need to find differential equations for theta and phi. Right now we have differential equations for the x's and y's, right? We have d squared x1 by dt squared equals stuff, right? So somehow we have to make that as a d squared theta or d squared phi of t equals stuff. So how do you do that? So we need to convert to go from d squared x1 by dt squared to, say, d squared theta by dt squared. And so the way we do that is we use what's called the transformation equation that we wrote. So let's box this equation here in red. This is the relation between x1 and theta, right? And so just to be explicit, theta and phi and x are all functions of t, right? So this is theta of t, this is phi of t. So they're functions of time. All right, so let's take our equation here. X1 equals we get plus L1 sine theta. And let's do d by dt of this. So d by dt of x1, so L1 is a constant, right? It doesn't change with time. So it's equal to L1 d by dt of sine theta. Let's be real explicit, it's sine theta of t. And so we're taking the derivative with respect to time of a function of the variable of time. Right, so it's the chain rule. So this course is all about the chain rule. So let's apply the chain rule. So we have L1, the derivative of sine is cos. So it's L1 cos theta, and then the derivative is of the inside of sine is d theta by dt. Right. So what we have in our four equations from Newton's second law is d squared x by dt. So we have to take the derivative again. So then d squared x1 by dt squared is equal to d by dt of this thing that we have up here. So that's L1 times d by dt of cos theta d theta by dt. So it's d by dt of a product. So it's a product rule. And then one part of the product, the cos theta, you will have to use the chain rule as well. Right? So everybody's familiar with the product rule for derivatives, right? The derivative of f times d is f prime d plus ds prime. So d prime x. All right, so let's apply the product rule here. So we have an L1 at front. So let's do cos theta. Let's take its derivative. So it's let's do it the other way around. We'll leave cos theta the same, and then d by dt of d theta by dt is d squared theta by dt squared. Right, and then so the derivative of cosine is minus sine. So then it's minus sine theta. And then because of the chain rule, there's a d theta by dt. And then I multiply again the d theta by dt. So it's d theta by dt squared. Everybody happy with that? You can do the same thing now with the x2, y1, and y2, again, taking the derivative with respect to time twice of the functions that we have up here, that allows you to get rid of all the d squared x's and d squared y's in favor of d squared thetas and d squared phi's. And then you can mix it all up together and you'll end up with two differential equations for theta and phi. And still on the fence whether I'll make you do that as an assignment. It's a bit like this. Okay, any questions about this? It's easy to look at you guys for questions, but any questions off-site? Okay. Is that so far, has it been legible off-site? Like the screen doesn't take too long to refresh, etc.? Good. I bought a Surface 3 Pro for Christmas in the hopes that it would make it much nicer. Okay, so let's see, what's next? Definition. All right. So that was just an example of a problem that's particularly annoying in analytic mechanics. Okay. Now, let's start setting up the framework. It's going to take a while to set up the whole framework for doing the analytic mechanics version. Today's lecture, we're going to introduce just notation and definitions mostly, and then next week we'll introduce a lot of math, and then we'll eventually get to the actual statistics. So we'll start with definitions and notations. So we'll define a particle to be a point mass that has a mass, and the location described by three coordinates. For example, x, y, and z. We'll associate a position vector with that particle. And that position vector, its coordinates are the three coordinates that I just mentioned. The rate of change with time of the position vector we'll call velocity. Okay. So we'll introduce v as the velocity vector, and that's dr by dt. And then similar, the velocity vector. We'll introduce a, the acceleration vector, which is dv by dt, also d squared r by dt squared. So the idea is that if for a given particle we know its position and velocity vectors and the forces acting on it, we can describe how it will evolve in time. So notation. We have a lot of d by dt's everywhere. In fact, even in the previous problem it was getting a little bit annoying to have d squared t's everywhere. So we're going to reserve the notation that d by dt of something. We're going to replace that by putting a dot. What I mean is our vector dot is dr by dt. So r dot is really v. And similarly, r vector double dot is a. We're actually not going to use v's and a's. We're just going to use r dots and r double dots. So remember, when there's a dot, it means d by dt. And then later we'll use a prime. Actually, you've already seen the use of prime in calculus, right? When you put f prime, you mean d by dx. You don't have to write d by dx everywhere. So it's the same thing, just for t. Okay? It'll be secondhand very quickly. Okay. So a rigid body is an object made of many particles that can't move with respect to each other. Let's say it's a collection of particles that are fixed with respect to each other. I'll try to get better with the writing big and writing small. It keeps changing. The new tablets, I have to figure out what the best Zoom is. So a rigid body requires 6 numbers to describe it. So a particle, right, requires 3 numbers to describe it, x, y, and z. So a rigid body can be described by the x, y, and z of the center of mass plus 3 rotation angles. Right? So if you want to describe like a complicated rigid body, think of a cube that has colors on different colors on each face. To describe fully its position in space, you have to say where its center of mass is, but you have to also describe how it's been rotated. And there's 3 angles that you need to describe how something is rotated. So a rigid body requires 6 numbers to describe it, whereas a particle only requires 3. That's the key distinction. Degrees of freedom. So degrees of freedom is the minimum number of scalar quantities that are required to specify the state of a system. Scalars needed to describe the state of a system. So we just did that example with the compound pendulum where there were 4 coordinates, 2 for each particle, but we saw that there's only really 2 degrees of freedom. They only need 2 scalars to describe fully that system. Okay? So a system is a collection of, let's say, n particles, capital M, and M, capital M, rigid bodies. So in general, a system has 3n plus 6m degrees of freedom. Right, so you want to describe a system that's made of m particles and m rigid bodies. Each particle requires 3 coordinates, and each rigid body requires 6. So a system would have, in principle, if there's no what we call constraints, would have 3n plus 6m degrees of freedom. Okay, so now constraints. Constraints applied to the coordinates reduce the number of degrees of freedom. We call that DOS. I'm going to write it out. So let's do an example of, let's show that as an example. Let's say, for example, we have two masses. M1 and M2 that are attached with a rigid rod of length L. So how many degrees of freedom? Oops. So in principle, there's 6 degrees of freedom is the maximum, right? Because there's 2 particles, and so 2 times 3 is 6. So we have 6 possible degrees of freedom. But we also have a constraint. So we can write this constraint as what we call a constraint equation. There's a constraint between the coordinates. So the constraint between the coordinates, the fact that the 2 masses are held together by this rigid rod, we can write as a constraint equation of the form, say, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared equals L squared. Where x1, y1, z1 are the coordinates of mass 1, and x2, y2, and z2 are the coordinates of mass 2. So you can see that by using this constraint equation, you can rearrange the equation to get rid of one of the variables, right? I can write x1 as the square root of all the other variables combined with L. So in principle, every time I have an x1 in my equations of motion or whatever, I can eliminate it in favor of all the other 5. So there are 5 degrees of freedom. Okay, so to find the number of degrees of freedom, you start with the maximum, so 3n plus 6m, and then for each constraint equation, you reduce the number of degrees of freedom by 1. So the number of degrees of freedom is equal to 3n plus 6m minus k for k constraint equations. Let's do an example. Example 1, 2. So let's say we have 4 masses. Labeled 1, 2, 3, 4. And in principle, the rods could be different lengths. So how many degrees of how many degrees of freedom does this system have? So how many constraint equations do we have? So we have 4 rods, so you can assume there's going to be 4 constraint equations. So let's write, say, for rod L1, we have that x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared is equal to L1 squared. Alright, so it's pretty easy to see that you get times 4. You get 4 constraint equations, right? 1 for each rod. It's a little bit actually unclear. So you have to assume here that the rods are allowed, the angle between the rods is allowed to change, essentially. So there might be less degrees of freedom depending on if the rods are allowed to flex or not. So you have to be a little bit careful with this one. So you'll see in the assignment, you'll specifically have to find out a good set of coordinates for them. But in the most general case, it's 4 constraint equations. So that means n, so the number of degrees of freedom, is equal to 4 times 3, that's the maximum possible, minus 4. So it's 12 minus 4, it should be 8 degrees of freedom for this particular problem. Is that what I wrote down? So what if the system is in 2D? Let's say this is confined to the plane of the 4 masses. Let's say that they're all in a plane and they stay in that plane. What is the number of degrees of freedom? Well, we could start from the beginning and we can say, now each particle only has 2 coordinates. So the maximum number of degrees of freedom is 8, 2 times 4, minus the 4 constraint equations, 8 minus 4, so 4 total degrees of freedom. Or you could just add in 4 more constraint equations, and those constraint equations would be that Z1 equals 0, Z2 equals 0, Z3 equals 0, and Z4 equals 0. And so then we find the number of degrees of freedom to be 12 minus 4 minus 4. So again, 4. So some of this can be done by just intuition, how many degrees of freedom, and some of it, but it can always be done formally by counting the constraint equations that you get from each thing. Okay. Any questions so far? All right. So let's move on to types of constraints. So there are various ways that you have constraints on the coordinates. So ultimately, the goal is to always have the number of degrees of freedom, that many coordinates, and then reduce that with the constraint equations to have the proper number of degrees of freedom. Okay, so it's always relations between the coordinates that we're usually interested in. So some definitions. Holonomic. A holonomic constraint is a constraint that can be written as an equation of the coordinates. So the constraint equation can be written using the coordinates. So the examples that we just did are classic holonomic constraints. The constraints are literally between the coordinates that they have to be separated by this distance. But there'll be other constraints to reduce the number of degrees of freedom that aren't necessarily obviously relations with the constraints. They have relations between the coordinates. Right. Let's do well, I guess I should note, because I know in the notes, the constraint equation that relates the coordinates to each other, that could depend on time as well. It could be that you have the 2 masses connected by a rod, so there's a constraint that the distance between the 2 masses is the length of the rod, but it could be that that rod changes length with a known function of time. So the constraint equation can depend on time. All right. So let's do an example of a constraint, and we'll see that it can be made holonomic. So example, rolling without slipping. Example 1-3. When rolling without slipping, we have this one-dimensional rolling without slipping. Yeah, let's call it one-dimensional. So our disk here, or whatever it is, can only roll along the one axis. It can't move around in the plane. Right? So in principle, if we want to describe our disk here we need two numbers, right? We need to specify, say, the x position of the center. Then we would have to specify, let's say, it's not a uniform looking disk, it has like colors on it, and so we have to also specify the angle about which it's rotated. So you would think that there's two coordinates that need to be specified here. But you know in rolling without splitting that x is related to phi, right? Because it rolls without splitting, so if you know where it is, you know how much it's rolled. So you know how many revolutions it's done, right? Two are constrained. So there's really only 1 degree of freedom, so you can choose phi or x. So how do you write that formula? So what is the actual constraint of rolling without splitting? So let's say this thing is moving with a speed, velocity, VCM, and it has a radius that we'll call little r. So the constraint of rolling without slipping is that the instantaneous velocity of the point of contact is 0. That's what rolling without slipping means. It means the velocity on the circumference there is 0, right? So the constraint, rolling without slipping, the constraint equation is that VCM scalar minus r phi dot is equal to 0, or that VCM is equal to r phi dot. I'm starting to use the dot notation now. So phi dot is d phi by dt, and so maybe you would call that omega. So this is just for rolling without slipping. If you look at the velocity of the point of contact, for it to be 0 means that VCM is r phi dot. Okay. So is this a holonomic constraint? So you agree that we have two possible degrees of freedom, but we only need 1 degree of freedom to describe the system. Now, holonomic constraint is a constraint between the coordinates. So the coordinates here are x and phi. But the constraint equation is between phi dot and VCM is x dot, right? So the constraint equation is actually an equation between the velocities, not between the coordinates. So it's not a holonomic constraint. This is not holonomic. Let's rewrite this. So explicitly this is x dot equals r phi dot. To be like super explicit, that's the same as saying dx by dt equals r d phi by dt. Now r doesn't actually depend on time, right? But it turns out this is trivial to integrate. So we can integrate this. So if we integrate with respect to time, we can get that x is r times phi. That's also what you expect, right? So you kind of knew ahead of time that x equals r times phi. But remember, the constraint equation is rolling without slipping is the velocity of the point of contact is 0. So that's not a holonomic constraint. However, in this particular case, we could integrate it and get a holonomic constraint. This is an equation that relates the coordinates to each other. So it allows us to take one coordinate and replace it with the other. So this is holonomic. Okay? Any questions about that? All right. So non-holonomic constraints. a non-holonomic constraint is a constraint equation that cannot be written as an equation between the coordinates. So rolling without slipping in one dimension could be changed into a holonomic constraint, but as we'll see in two dimensions it can't. So either doesn't contain the coordinates in the constraint equation, or contains an inequality. So it could be a constraint equation that does indeed relate the coordinates to each other, but it's an inequality rather than an equality. That would also be non-holonomic. So an example of that, example 1.4, you have a bunch of particles constrained to be in a sphere. So the particles could be gas molecules, and those gas molecules are contained inside of a sphere. And the constraint equation is that xi for each particle I squared plus yi squared plus vi squared must be smaller or equal to r, the radius of the container. So that is an equation that is between the coordinates, but it has an inequality, so it's not holonomic. R squared. And finally, this one's absolutely horrible to draw. Example 1.5. This is rolling without slipping in two dimensions. The drawing in the notes is slightly better than what I'm going to probably end up doing here. So let's draw a sphere. And the sphere is on a plane surface. So the sphere here is touching the plane, the XY plane, and constrained to roll around on the XY plane. But so far it's understandable in my diagram, right? So it's rolling, and let's say it's rolling in this direction here. So this is going to be the direction of motion along the plane, so that this vector that I just drew that's not very straight is in the XY plane. Okay? And so in the XY plane, that vector, if I draw something parallel to the x-axis, makes an angle which I'll call theta. Okay? So theta tells me which direction the ball is rolling. If the ball changes direction, theta changes. Right? Now I introduce phi. Phi is the angle of rotation of the ball. Right? So the ball is moving along this path that the vector, And then a distance along that path, let's call that ds. A distance in the direction ds is going to be equal to r d phi. Right? So the constraint is again the same, right? The constraint is that ds by dt is equal to r phi dot. Now remember, the sphere, we're going to describe it by, let's say, the x and y position at the center, so the point of contact, and then phi. So this cannot be integrated. So we get ds is equal to r d phi. And if we want to use our coordinates x and y, so remember ds doesn't tell us where the sphere is, right? ds is not a coordinate of the sphere. ds is just the sphere is going in that direction and it's moved the displacement ds. So specifying ds doesn't tell us anything about the position of the sphere. So this ds equals r d phi or s equals r phi, so that easily integrates. That still doesn't give us an equation that relates to coordinates, right? It doesn't relate x and y, which does describe what the sphere is, to phi. Right? So you can't integrate this ds equals r d phi because along that axis it's one-dimensional motion. Right? This doesn't tell us which way ds is pointing. Right? We need to know which way ds is pointing. So for that, we'd have to write, say, dx is equal to ds cos theta, and dy would be ds sine theta. And so that means we'd have to write dx is r d phi cos theta, and dy is equal to r d phi sine theta. Okay. You can't integrate these together. What should I write that? Cannot integrate to get equation relating x, y, and phi. So rolling without splitting in 2 dimensions is not a holonomic constraint. One way to think of it is, depending on the path it takes, it can come back to the same position in x and y on the plane, but having rotated different amounts in phi. It's the common thing with the rotating the sphere and confusing yourself to which way it's pointing. It's possible to take different paths, end up at the same point, and have actually the sphere at a different rotation than it was initially. So it's somewhat intuitive that you can't get a holonomic constraint out of it. X, y, and phi are somewhat independent. All right, so that's an example of a non-holonomic constraint. Add some more complicated words. Scleronomous constraint. Scleronomous. That's a constraint that does not depend on time. So that's a separate property from holonomic and non-holonomic. It's scleronomic. So you have a holonomic scleronomic constraint. Okay. So that means you can write the constraint equation. When I say it doesn't depend explicitly on time, I should say doesn't depend on time explicitly. But we have to be careful between when we say implicit and explicit when we say that something depends on something. Right? The bars, let's say the most simple example is the two masses connected by a bar. That's a holonomic constraint. We know the positions of the masses, they're related to each other. The distance has to be equal to the length of the bar. But does it depend on time? It kind of does, right? Because let's say the bar is moving, then the position of the particles changes with time. So that equation does have time in it. If you actually want to calculate it, you'd have to put the time to know which position each particle is in. So it depends implicitly on time, but it doesn't depend explicitly on time. So that means that if you take the partial derivative of the equation with respect to t, you get 0. In other words, t isn't written into the equation. So it's a function of, the equation has functions that depend on time, but it doesn't have time itself in it. And you can always check that by taking the partial derivative with respect to t. So if you do di by dt of something, you'll get 0. But remember, the sig d by dt of the constraint equation, you're not going to get 0, right? Because dx by dt is not 0. So it's something you have to be a little bit careful. And this will come up a lot, and it'll be secondhand to you when we talk about explicit and implicit time dependence. So this is the first time it comes up. Okay, so then, of course, then there's the other one when it does depend explicitly on time, and that's called reonomous. So that's a constraint equation that depends explicitly on time. So again, like with the example of two masses, the dumbbell connected by a bar, let's say that the bar changes the length of time, the two masses are still constrained. You still can describe one by knowing where the other one is, but the constraint equation depends on time. So that's just a real number. And we'll see in this eventually that certain systems that are scleronomous or reonomous or holonomic have desirable properties. The time dependence, although it sounds scary, is actually not a big deal. It's the non-holonomic that's a huge pain. The holonomic systems are very easy. Whether or not the equations depend on time is usually not so important. Now what's important is that they're holonomic. And you can think of it, right? Just the sphere is already a page, and it's a non-holonomic thing. So in general, non-holonomic things we will mostly ignore. All right, so generalized coordinates. Oops. Was there any questions so far, or maybe from the people off-site? Okay, so generalized coordinates, the idea is that we start by describing a system with the x, y, and z position of every particle and rigid body in there. Then we apply constraint equations, and we end up with a more limited set of coordinates or numbers to describe our system. And so that limited set is what we call generalized coordinates. Okay? So usually the minimum number of coordinates after constraints to describe a system. So if, let's pretend there are no rigid bodies. So let's say for n particles, and k constraints, the generalized coordinates will be a set of numbers. We're going to use the letter lowercase q for coordinates. So it'll be a set of numbers q1, q2, all the way to q3 n minus k. And these qi are functions of time. Okay, so in the example that we did earlier with the compound pendulum, we had initially 4 coordinates, x and y for both masses. There are actually 2 constraint equations, right, because there's the 2 rods. The one mass is constrained to be a certain distance from the origin, the other mass is constrained to be a certain distance from the first mass. So that's 4 minus 2, so that's 2 degrees of freedom. And then we had a liberty in choosing what those 2 coordinates would be to describe our system. So those are the generalized coordinates, q1 and q2, and we chose theta and phi as our q1 and q2. Okay? So these generalized coordinates, they could be theta and phi, or they could have been x1 and y2. But they could have been something more complicated, like the position of the x position of the center of mass, and some other weird thing. So they could become pretty weird. They could even not even have units of distance. In fact, angles don't have units of distance. So they could be something quite complex. So we're going into a much more abstract representation of classical mechanics. And so this is one of the tools that allows us to abstract this description. So think of a system as you need n scalars, so the number of degrees of freedom scalars to describe that system. Those scalars we're going to call generalized coordinates q1 to q little n, say. And then that's what the generalized coordinates are. And in some cases they will be quite abstract, and in some cases they will just be x, y, and z. So we'll just call them q because it allows us to be a little bit more general with that. Okay? So in general, we would know the transformations between generalized coordinates and, let's say, the original coordinates. So that means, for example, we would know x1, we would know how it depends on q1, q3 n minus k, and potentially t. Right? So x1 would be the particle 1. X, let's say y1, we would know what function of the q's that is. And then we would know that for all the particles. We did this with the compound pendulum, right? We wrote out the 4 equations that relate x1, y1, x2, y2 to our 2 generalized coordinates, theta and phi. Remember? So we've done an explicit example of this, but here's the sort of formal description of it. So, so we can also, from this, we can find what we call the generalized velocities, in principle the generalized accelerations. So because we know these transformation equations, we can take the time derivative of those transformation equations, just as we did for the compound pendulum, right? So for example, we find that x1 dot, so now it's the chain rule, so x1 is a function of q1 to q3n minus k, which are all functions of t, and then a function of t itself, right? So x1 dot is given by the partial derivative of x1 with respect to q1, and then because of the chain rule, times q1 dot. That's going to be the sum over all of the generalized coordinates. So I don't know if this is, I thought it was common, but I had questions last semester. So if it's a partial derivative, I'm going to say di x1 by di q1. So if I say di, I mean partial derivative. If I say dx by dq, I mean total derivative. Okay. So every time I say di, I mean di. Okay. So then I mean partial. So the dx1 by dt, which is x1 dot, is di x1 by di q1 dot plus all of them di x1 by di qn 3n minus k q 3n minus k dot, and there's a term at the end there, plus di x1 by di t. Because in principle the x1 could depend explicitly on t. And so there's a term at the end of di x1 by dt. That comes from writing that dx1 is di x1 by di q1 dq1 plus di x1 by di t dt, right? A small change in x1 is, because of the chain rule and the partial derivatives, is the di x1 by di q1 times dq1 for all the things that x depends on, including t. So there's a term t at the end. And if I want dx1 by dt, I'm basically dividing the t out of this equation. So you're left with, so you have a dx1 by dt on the left, you have a dq1 by dt, and then the last term ends up as just a partial derivative of x with respect to t. Okay? So that's the generalized velocities. I think we can finish the chapter, right? So let's finish the chapter. So let's do an example. This is example 1.6. So we're going to write out the generalized coordinates to describe the motion of a bead of mass m that's constrained to slide along a massless length of zone L that is rotating at a constant angular frequency omega. Write out the constraint equations and the generalized velocity. So the system is we have this bar here that's massless, and it has a length L. It has a stop at the end of it. We have our particle of mass m on it. I've drawn in the notes, for some reason, a y-axis going down and an x-axis going left. Maybe this is seen from above, and z is 0. So this is rotating in the horizontal plane. This has a total length L. and then it's rotating with an angular frequency omega. So let's say that this angle here, theta, let's say that theta is omega. So the question is, how many degrees of freedom do we have here? So it's a 2D motion, so in principle there's 2 degrees of freedom, the x and y position of the bead. Now we're told the bead is constrained to move on this rod, and the rod is going at a fixed known angular velocity, omega. So there's only 1 degree of freedom, because just thinking of it, at any point in time, we know where the rod is, because we can just calculate omega t, and so if we specify x or y, we can know the other one, because it has to be on the rod. So this suggests that we can use one generalized coordinate, and we should choose what's a good generalized coordinate to use here. So this has 1 degree of freedom, and so let's choose r as our generalized coordinate. Alright, so by r, I mean the distance of the bead from the origin. Alright, so theta is always given, so we can always specify where the bead is by specifying just the one number r. So the transformation equation, so now r is a function of t, right? Okay, so let's write out the transformation equation. So remember, our starting coordinates are x and y. So we want to know how x and y relate to r. So x is t. Let's just be explicit and say and point out that x is a function of t. That's equal to, based on this diagram, it's minus r sine theta, minus r sine of omega t. And then y of t, in this case it's going to be positive r cosine omega t. Right? The constraint equations so we have z equals 0. We want to reduce this from 3D to a 2D problem formally. And then we also have that tan of omega t is equal to minus x over y. All right, that's that constraint tells us that the bead has to be where the rod is. So that relates x and y. Now there's also an additional non-holonomic constraint. And that's that x squared plus y squared has got to be less than L squared. We can't use that to reduce the number of degrees of freedom in this case, because it doesn't really tell us anything. And finally, let's calculate the generalized velocities, or find how to relate the velocities of our original coordinates to the velocity of our generalized coordinate. So x dot is d by dt minus d by dt of r sine omega t. So r is a function of time, right? So it's going to be minus r dot sine omega t, so I'm using the product rule, and then minus r, the derivative of sine is cos omega t, and then times omega from the chain rule. Right? And then similarly, y dot is d by dt of r cos omega t. We're doing the product rule, so that's going to be r dot cos omega t, then r times the derivative of cos, which is minus sine, so it's minus r sine omega t omega. So this might not be super obvious why we want to know what x dot and y dot are, but later we'll need to know the kinetic energy of the system, and that kinetic energy depends on x dot squared and y dot squared, right, because it's v squared. So this will allow us to write the kinetic energy in terms of our generalized coordinate r, or r dot. Alright, and then the last, oops, you guys done copying that? Any questions about this? Okay, so the last thing is the definition of what we call configuration space. So the lowercase n generalized coordinates can be used to create an n-dimensional configuration space. So like you have one particle in three-dimensional space, configuration space is the same as space. But you could think of, you have two particles in 3D space. You can define that system by specifying 6 numbers. So you can imagine a 6-dimensional space where a point in that space defines the position of the system. In that case, it's 6 numbers and it specifies 2 different positions. Right? So then, a point in configuration space completely describes the current state of a system. But it doesn't tell you where it's going to go. So you need to know the velocity in configuration space as well as the laws of motion, so what forces are acting on the thing, to know where it's going to go. And so that's the key thing about configuration space, is that the location in configuration space tells you what the system looks like, but it doesn't tell you where it's going to go. This is in contrast to something that we'll see later on in the course called phase space, where there the position in phase space tells you both the current system, the state, and where it's going to end up. Okay, but that's for a few months from now. So that's all I had for today. Next week, it'll be all through Blackboard. I'm actually not even going to be here. I'll be at the Center Underground Research Facility underground. So if you have any issues, please contact me. And make sure, maybe the first few times to get used to connecting, maybe connect a few minutes early just to make sure you don't have any issues. Okay, but that's it. Thanks, everyone. Any questions from the offsite? What's going on? I'm going to stop the recording.